In this video, we introduce ourselves to chemical bonding and look at the three main types of bonding we see in elements and compounds, namely metallic bonding, ionic bonding, and covalent bonding. When atoms or ions are strongly attracted to each other, we say that a chemical bond exists between them. Chemical bonds are strongly attractive forces that hold together atoms in complex units, such as in molecules or in ionic compounds. Chemical bonds involve the interaction of valence electrons from the combining atoms. The electron configuration and electron distribution therefore play an important role in chemical bonding. Chemical bonds may be the result of the electrostatic attraction between particles of opposite charges, such as in metallic bonds or in ionic bonds, or they may be the result of sharing of electrons, such as in covalent bonds. In all cases, it is the interaction of valence electrons that defines the nature of the chemical bond. Broadly speaking, there are three types of chemical bonds that exist in chemical substances: metallic bonds, ionic bonds, and covalent bonds. Metallic bonds are formed between atoms in metallic elements, such as in copper or gold or any other metal from the periodic table. Ionic bonds exist between positively charged cations, usually metallic in nature, and negatively charged anions, usually non-metallic in nature, and the classic example being the compound sodium chloride or good old table salt. Covalent bonds exist between non-metallic elements in molecular substances, and the classic example there being water or H2O. In the reaction between elemental sodium and elemental chlorine to form sodium chloride, all three types of bonding are evident. Metallic bonds hold the atoms together in elemental sodium. Covalent bonds hold the atoms of chlorine together in the Cl2 molecule. And the sodium ions and chloride ions that are formed during this chemical reaction are held together by the electrostatic ionic bond. So let's have a closer look at all three types of bonding, starting with metallic bonding. Metallic bonding can be described in terms of the electron C model, which describes the attraction between atoms in metals. In this model, the metal is pictured as a regular arrangement of metal cations in a sea of mobile valence electrons, as depicted in this diagram. The metal cations are actually comprised of the nucleus of an atom and its inner or core electrons, whereas the sea of electrons is comprised of mobile valence or outer shell electrons. These negatively charged valence electrons are confined to the metal by the electrostatic attraction to the positively charged nuclei, and they are uniformly distributed throughout the three-dimensional structure of the metal. The valence electrons are considered to be mobile, and no individual electron is confined to a particular metal nucleus or metal ion, and in the presence of an electric field they can become highly mobile and show a net flow through the metals towards the positive part of that electric field. This model is adequate to explain chemical properties such as the ease of formation of cations, as well as the physical properties of electrical conductivity, thermal conductivity, malleability, and ductility, although it is somewhat limited when it comes to explaining trends in melting points of metals. An ionic bond is the attractive force that exists between ions of opposite charge, and specifically describe bonding that occurs in ionic compounds. Now, one way that an ionic compound can be formed is through a chemical reaction of its constituent elements involving electron transfer. And as an example, we'll consider the formation of sodium fluoride from elemental sodium and elemental fluoride. Now, the neutral sodium atom contains a total of 11 electrons, 2 in the 1s subshell, 8 in the n equals 2 shell, which are spread across the 2s subshell and the 2p subshell, and the last electron is in the 3s subshell. This gives an overall electron configuration of 1s2, 2s2, 2p6, 3s1. The neutral fluorine atom has 9 electrons in total, 2 in the 1s subshell and 7 in the n equals 2 shell, spread across the 2s subshell and the 2p subshell. And this gives an overall electron configuration of 1s2, 2s2, 2p5. When the two atoms come in close proximity together under the right conditions, the 3s electron from sodium can be transferred to the outer shell of the fluorine atom, giving both atoms a full complement of electrons in their outermost shell, which we know is a stable electron arrangement. Of course, during this process of electron transfer, a positively charged sodium ion is formed and a negatively charged fluorine anion is formed, and the electrostatic attraction between these ions of opposite charge constitutes the ionic bond, which holds these atoms together in a semi-infinite three-dimensional lattice. Now we can represent this electron transfer process in a different way using a chemical equation that includes the electron configurations of each atom. For example, we can see that the 3s outer shell electron from sodium is transferred to the outermost shell of fluorine, resulting in a sodium ion with the stable neon core and a fluoride ion that has a helium core plus 2s2 2p6, which we know also happens to be the electron configuration for neon. Now it's important to note that the formation of ionic compounds can also occur from already existing ions where the electron transfer process has already taken place. In fact, this is by far the most common way that ionic compounds are formed. An example would be the formation of the solid precipitate silver chloride, or AgCl, from a solution of silver nitrate and sodium chloride. In precipitation reactions such as these, the formation of ionic compounds depends on the solubility of certain ions in the presence of other ions. In order to predict the formation of ionic compounds in this way, we need to refer to our solubility rules. A covalent bond results from the sharing of one or more pairs of electrons between atoms. The electrons that are shared between the two atoms are valence electrons, which are attracted to the positive nuclei of both atoms and therefore linking them. A covalent bond is therefore defined as the attractive force that results from two nuclei attracting the same shared electrons. And in the covalent bond model, atoms share valence electrons in order to achieve a favourable electron configuration. For example, we see that a single hydrogen atom has a single 1s electron in its electron cloud, which we know is not a stable arrangement. By sharing an electron with another hydrogen atom in forming the H2 molecule, each atom can now be said to have two electrons surrounding its nucleus, and this is a much more stable electron configuration. For example, if we think of the electron cloud of helium, which has two electrons around its nucleus. As I said before, the covalent bond model involving electron sharing is used to describe the attraction between atoms in molecular substances. As another example, we could consider the formation of the F2 molecule from single fluorine atoms. A single fluorine atom has 9 electrons in total, with 2 inner or core electrons, plus 7 valence electrons in its outermost shell. The electron configuration, 1s2, 2s2, 2p5, is not stable. By bringing the two fluorine atoms together and sharing 1 electron from the valence shell of each atom, the F2 molecule now has 8 electrons surrounding each atom in the outermost valence shell, and it has a total of 10 electrons overall. And this is similar to the electron cloud of neon, which we already know is a noble gas and therefore represents a stable electron cloud. A third example, this time involving a polyatomic molecular compound, water, or H2O, shows that the sharing of 1 electron from each hydrogen atom with the outermost shell of the oxygen atom results in all 3 atoms achieving a stable configuration, with both hydrogen atoms now having 2 electrons in their electron clouds and the oxygen atom having 8 electrons in its outermost shell or valence shell. In the next video, We will see how this propensity for the formation of 8 electrons in the valence shell of atoms within bonds is generalized via the octet rule, which is valid for many common atoms. We will also see how the use of Lewis symbols in the creation of Lewis structures allows us to readily track valence electrons of atoms, and we will be introduced to the concept of electronegativity, which assists us to explain how electrons are distributed around atoms in chemical bonds.